Great. So thanks a lot for the opportunity to present my work in this amazing platform. This is joint work with Juan Pantano, and I guess some of you know that we have been working on this paper for more than a decade. We started working on this more than 10 years ago, and for various reasons, the project went on a hiatus. But now it's very much back to our minds and on our desks, and we are trying to finish it. So at this point, any comments would be highly, highly appreciated. Okay, so given the audience today and also the very helpful introduction we just heard from Tan, who makes my life much easier, I'm just gonna start by saying that by the very nature of the CCP estimators, it is not very straightforward to accommodate permanent unobserved heterogeneity in the estimation strategy. And people have been thinking about this problem for a while, and at a very high level, what we are gonna propose to do, share some similarity with, in particular, this recent contribution by Bonhomme, Lamadon, and Maresa, in the sense that we would like to append to the Hotz-Miller strategies a pre-estimation stage where we classify the observations into different groups so that we can run Hotz-Miller on homogeneous groups. That's a very simple idea. The difference is that we propose to use expectations data to achieve this first stage of type identification. Okay. And as many of you who work with expectations data would know, expectations data are quite noisy. So we're gonna discuss an ideal case where these expectations are elicited precisely. So you give precise probability of the chance that you take a certain action in the next period, but then we extend to a scenario where there is a particular form of measurement error. So your expectations are going to be rounded off to some focal points. And we show how we can generalize our idea to this more realistic form of expectations data. So I'm just going to focus our mind by repeating the very useful model of engine replacement. And I'm going to first discuss the identification in a more restricted form of unobserved heterogeneity that would imply the model satisfies a monotonicity property. What that means is that the conditional choice can be ranked by the types, and the ranking of those conditional choice probabilities are going to be stable across types. So if that is true, then we can show with a single self-report of expectations of your action in the future, you can achieve type identification. And then moving to a more general case where we allow more unrestricted types of unobserved heterogeneity, we need 2 self-reports to achieve that. So let's just jump right in. I believe many of you have seen this model many times, so I'm going to be really quick. Let's say there is a machine, the state variable is the age of the machine, right, xt, and every period the firm or the owner makes the decision whether to replace it or not, given the age, right? If you don't replace it, so d is 0, then the profit follows this function where theta measures the maintenance cost or depreciation if you want. And if you do replace the machine, then you pay a replacement cost of R. And then on top of that, there is also the type 1 extreme value shocks to these discrete choices. And then we allow the machine to age stochastically. So with some probability, if you don't replace it, it ages by 1 year. Otherwise, it stays where they are, capped by age of 5. So it caps the value xt can take. And then if you do replace the machine, then it's age 1, right? So let's imagine on top of that, we have a survey that runs for all the owners of the firm that asks them once, what is the probability? So given the age of the machine, after you've taken the replacement decision today, you ask them what is the probability that they will replace the machine next period. Okay. Imagine we have this additional source of information about subjective beliefs of future, but the probability of future actions. Okay, we're going to show with this additional data, we can identify some form of unobserved heterogeneity. Okay, so let's start from a simple case. Let's assume there is just a single dimensional unobserved heterogeneity in the replacement cost. Let's say there is a time invariant discrete type indexed by k. Okay, so then we have cap k types of machines with different replacement costs. Okay, and because the simplicity of the model, we can easily establish that the lower types, which have higher replacement costs, replace machine less likely in any state, right? So the ranking of the probability of replacement given an age, right, by type is going to be stable across all ages, right? The low type just replace it less likely because it's more costly for them to do. So when this is the case, we say that the model satisfies a monotonicity property, which just means that this ranking is stable across all types. And then we show how we can identify those types with a single self-report. Okay, so what is this self-report? So
subset of X's, specificity, you have like a local version. I guess you could use then just use the method on that subset. So right now you need this tool for all states of the world.
You see why I need that. Okay. Yes, I need that. I do need that because we only have one self-report at this stage. Okay, if we have more than one report, we don't need. You see. Okay, so once you heard that question, what's the chance of replacing the machine next period? We assume that Mr. Zucker is going to calculate with the solution of the dynamic programming problem, the probability of the CCPs for every state. And then I'm starting from current state, current choice. What's the correct transition into the next states? And I'm going to calculate essentially the 1 period ahead expected CCP and report it with great precision. Let's suppose in the ideal case, this is what Mr. Zucker does. And then the basic intuition is really simple. Yes. Yes, everything is true. Everything is, but yes, Mr. Zucker knows F and it also knows the true RK. He knows his type. We don't. Yeah. Okay. So then the basic intuition is really simple. If you have two engineers or owners who are at the same state, so same age of a machine, and makes the same decision, replace or not replace, and then you ask them 1 period ahead, expected CCP, and their answers are different, then there must be something that's not observed by us, but by them that makes their answers different, right? So just by virtue of different answers, we can say these two people operate machines of different types. On the contrary, if they say exactly the same probability, then with probability 1, we can say that they are of the same type. So the core intuition is just as simple as that. And you see a variation of how to use it in more complex situations later. So in this case, actually, if we have full control of the GDP, DGP, we will see exactly K different self-reports in a particular state choice combination XD, right, from our example. And we can rank them from lowest report to highest report, and then the ranking reveals their types by monotonicity. Okay, so this is why we need the monotonicity, because we can only compare reports at the fixed state choice cell XT. So it has to hold for every XD combination. Okay, so if CCPs can be ranked, then the expected CCPs can be ranked, and the ranking will preserve the type. Okay.
identification of type, if it's just one of the subset, would you just do the identification of types in that subset of states?
I'm gonna do a more general version of that when we have two reports.
Okay.
And I think, yeah, you'll be happier then. Of course, in reality, we don't have precise elicitations. And if you look at any expectations data, they usually bunch at some focal points, right? So 0.5, 0.25, 0.75, these are more salient points that people report. So then we consider a particular form of measurement error. So we still assume that these agents solve the dynamic problem and they have the precise number, but they only round it off to the closest focal point that we recognize. Okay. Now, this by itself may not introduce any problem because, as you saw just now, we don't really use the information of the number, right? We just need the types to be sufficiently different in the number they report. So if the focal doesn't introduce bunching in the sense that two types give the same answer, then it's completely innocuous. We don't really care what number they give as long as different types give different numbers. But in the case where there is bunching, then we're in trouble. So we are gonna provide a practical way of dealing with this. And at this point, I think we welcome comments and suggestions on this idea that we have, and we are working on it. So let's suppose we recognize B focal points in the data. That means at most we can have B types, right? Only B different answers, that's possible. Then if you look across state choice cells, so XD cells at the time of report, the number of types big K is gonna be pinned down by the state choice cell that has the largest number of different answers, right? That's the maximum number of types you can identify. Now, if that's true, then you look at all the state choice combinations, XD, and then where you have K different answers, then we say in that state choice combination, the types are fully expressed. So you just rank their answers. The lowest is type 1, second, type 2, all the way to type K. Drop down, right? But in the state choice cell, XD, where we have fewer than K different answers, then we have to work out which answer belongs to which type. We can rank them, but we don't know the exact mapping because the lowest answer could be type 1 or could be the bunched answer between type 1 and 2 or type 1 to 3 and so on and so forth. So here we are proposing an iterative procedure to deal with it. Yes. No, so we have to assume that K is less than B though.
Yes.
But we can infer K by looking across XDs and pick the XD that has the most largest number of different answers. I guess so in the application that we had been working on, we are basically take every 5th percentile. That gives you 21 different types possible maximum, which I think is more than most applications that has this type of types. So, okay, so now let's divide the sample into 2 subsamples. In the first subsample, we collect all the observations where at the time of the question, their state choice cell has all types fully expressed. Then we can just infer the type for them. So we have one subsample where we know exactly what type of these observations are. And then we have the complementary example that's problematic. So first of all, we compute type-specific CCPs for the first subsample where we know the types. We will try to compute CCP for as many states as possible. And when we have missing information for some states, we go to the full sample and compute incorrect CCPs by averaging out the types and then fill those holes in. Okay, we'll estimate the sample separately by type. So the parameters are the K type specific replacement cost plus some parameter that's common across all types. And then we call the estimates the first iteration estimates. 1 is the first iteration. And then with this, I mean, obviously this is incorrect because we have some round CCPs there, right? And then we are going to calculate what is the model implied CCP or 1 period ahead expected CCP for any state choice and K combination we want. Then we're going to go back to the subsample where the types are indeterminate. And then we're going to see for this particular observation who reports at XD, what would his type be if what would his report be if his type is 1 according to our model? And we do the same. We can ask what would his report be if it's type 2 or 3 or 4, right? And then we're going to assign a type by minimizing the distance between the model implied 1 and his actual report. Yes. So every firm gives 1 report as certain state choice cell, right? So given a state choice cell, we collect all the firms that make report on that state choice cell. If there are K numbers of different answers, then we know the smallest answer corresponds to type 1, the largest type K. We know the type of all these observations. This is our first subsample. So we know the exact type of the observations in our first subsample. And the rest is problematic. Great question. Here we assume we have a lot of data. So I guess if you have infinite data and if the model is such that you will eventually populate, I guess with extreme value shocks, you will, or the state space, then in fact, we will not actually get to a stage where there will be holes in the first subsample, right? If we have limited data, then there might be holes in first subsample. Yep. Yes. Yes, either bunched or some type never really visit that state choice combination, and hence you don't have a report from that type if we have limited data. Yeah. So, but we don't really know which is the case. And hence this more practical iterative procedure that we are working on and trying to implement in the Monte Carlo. Okay. So then by the end of the first iteration, we can assign types for everyone in our sample, right? Because we compare the actual report of these problematic observations with the model implied type 1, 2, 3, 4 reports, and we pick the type that is closest to the actual report. Then we can have a tentative assignment of type for everyone in our sample. We divide the sample by type. We run Hotz-Miller on each subsample. Then we have this second iteration of structural parameters. And then we do the same. We do the model implied CCPs, expected CCPs. We look at the problematic observations. Then we try to reassign their types, and then we iterate it until there's no more reassignment from iteration to iteration. At that point, we stop. So that is our proposal for dealing with the problem under monotonicity assumption, and we're working on a Monte Carlo based on this idea. I think so. In principle, as long as the difference in the state transition does not exactly offset the difference in the CCPs later on, so that you report the same, then we can definitely allow type-specific transition as well. Yeah. Yes. You can, because as you see, our procedure has no econometric foundation. So it's motivated by practical concerns. So this is definitely something that one could do. In fact, we tried a different procedure later on in a more general model where we form a system of equations using expected CCPs and try to recover the type-specific CCPs and construct the posterior belief of type K given your choices and states, and try to use that as a tentative assignment. So yeah, you can do lots of different procedures. We thought this is simple, but we have yet to prove the effectiveness of this. But I guess one idea is to try different procedures to see if they lead to the same result in a real application. So with a very simple example, I hope that I have illustrated the core idea, but obviously most models don't have this monotonicity property, and therefore it's useful to think what we need to do once we relax this assumption. So now we're going to consider this alternative way of introducing unobserved heterogeneity. Now both theta, the maintenance cost, and the replacement cost are type specific. Once this is true, we lose monotonicity. Okay. Imagine two machines. One depreciates faster, but is also more costly to replace. Then when the machine is relatively young, okay, the probability of replacing that machine will be low because the high replacement cost is very salient at the beginning. Now, when the machine ages, the probability of replacement actually becomes higher because then the maintenance cost becomes more salient. So there you have crossing in the CCPs across two types. You no longer have monotonicity, right? So what do we need to do in this case? We show that with two self-reports of subjective expectations, we can still restore our ability to identify which machine is the same type as another one. And this is how it goes. Imagine we're in a case where we have exact, precise reports. Okay, that's an easier case. Now let's say we have three machines, A, B, and C. Okay, so for machine B, we have two reports elicited at two different state choice cells, XD and X prime D prime. Okay. And let's say we can link machine B to machine A because they happen to report the same thing at state choice cell XD. Okay. Let's also say we can link B and C because they report the same thing in the state choice cell X prime D prime. Then we say A is linked to C, even though A and C never report in a common state choice cell. Right? So it's a variation of this idea because we can only identify whether you're the same type whenever you actually visit the same state choice cell. Then we need at least two reports to be able to link people so that eventually we can link two different firms, even though they have nothing in common. So we call it a linking technology. Mathematically, it's just a form of defining an equivalence relation. Let's say, let's define a binary relation between two observations, I and J. We say they are related if there is a common self-report. And think of self-report as a triplet. It's a common XD and the same answer. Okay, it's a triplet. Now, if this is true by the argument, because it's precise elicitation by the argument I made before, these two observations have the same type, right? Now we say I is linked to J if we can find a subset of observations where we can do this pairwise link. That's it. Okay, we can check this is an equivalence relation, and therefore it partitions the sample into subsamples. Now the question is whether the subsamples, so this partition, corresponds to the partition in terms of types. Okay, so to establish that, we need an additional assumption, which we called self-report no islands, which essentially means if you pull all the state choice combinations at which type K reports, then you cannot have a scenario where some observations report on one island of that space of XD and others on an island, and there's no link between two islands. Maybe to appreciate that assumption, I give you an example where it fails. Let's say you're working with biennial data, and you ask correspondents, what's the chance of you dropping out of school next year, okay? Now you have a bunch of kids reporting at the age 14, 16, 18, and you have a bunch of kids that reports at the age 15, 17, 19. There is no way to link these two if age is a state variable, right? Even if those kids have the same type. So whether that assumption is satisfied or not depends also on the design of the survey, if you want. But if it is satisfied, then we can establish that the linking technology we defined above establish the type precisely. Okay. And the, okay, yeah. So I'll skip the proof. Now let's move on to the focal case. As I said, if focal self-reports do not necessarily bring us trouble. It brings us a trouble when there is bunching, meaning two different types report the same focal point, right? So we say when two focal self-reports, so SRF, they're said to be bunched at a certain state choice cell if there are two observations of different types but report the same in that state choice cell. Then we say they are bunched, okay? This means if you see different reports at a common state choice cell, you know they are different, but when they are the same, you actually are not sure whether they are the same type or not, right? Therefore, we need some revelation of bunching. So the first assumption we need is that for each bunching of a type, we need at least some observation that tells us there's a bunch. So you're going to see a lot of graphs in this form, so let me take a moment to explain what it is. So this horizontal axis is lexicographic order of XD combinations. So this observation I reports 50% in this particular XD combination and reports 80% in a different XD combination. Now these two observations reveals the bunching at the first XD choice, because in the second XD where they reach and they report different answers tells us that they are different types, but then they report the same in the first XD. So it tells us that there is bunching going on in the first XD combination. So this assumption says whenever this happens, whenever at a certain state choice cell there is type bunching, there needs to be at least two observations that tell us it's happening. Otherwise, we don't know. Okay, so that's the first assumption. But with this assumption, it's not enough to identify types. Considering this graph, forget about the colors yet. So obviously, by looking at observation J and G, we know that this is a bunching state choice cell. We also know that I and H are different types. Okay, but we only know these two are different and these two are different. We don't know whether I and J are the same type or I and G are the same type, right? We only know that pairwise they are different. So in this case, we need a third observation that tells us who belongs in the same group. So this is the second assumption we need, which is, we call it the bridging assumption, that says whenever there's a state choice cell that has some form of bunching, then you would need a third observation that provides answers in the non-bunching state choice cells that tell us that this is one group and the other branch of the bunching is a separate group. Okay. So that's the second assumption we need. third assumption, notice if we have two observations, right? So in this example, one of their state choice cells is bunched because it's revealed by these two observations, right? Now, by virtue of bridging, we will have a bridge if, let's say I belongs to type 1, we'll have a bridge here that tells us this is the same type. But if this state choice cell is also bunched state choice cell, meaning that type 2 also provides an answer of 0.5 in this state choice cell, then we would have another, right, bridging that reveals, with the two bridges, reveals that this state choice cell is also bunched 1. And in this case, we will never know whether I belongs to type 1 or type 2, because everyone who reports in these two bunched state choice cells, we can't identify their types for sure between 1 or 2. So we need to rule out this case by requiring that one of the self-report is made in a place where there's no bunching. Now, with these assumptions, okay, we can modify the definition for the equivalence relation and then reestablish identification of types. So this is how the relation works. We say I is related to J if there is one common self-report, okay? And if that self-report occurs at a state choice cell where we know there's bunching because of assumption 1, whenever that happens, it's revealed, but by observations who don't necessarily involve IJ, can be revealed by G and H, let's say. But at least we know, then we say we look for a third observation that bridges them. Then we can say they are linked. And then the second half is the same. I is linked to J if we can find intermediate observations that link them pairwise. So with these assumptions, so with B1, which says whenever two type bunch in a XD, we need some observation that tell us that happens. And whenever that happens, we need the bridge to tell us which arm of the bunching, right, we are working with. We have assumption B3 that tells us we can't have two bunched XD cells simultaneously. If that's true, and also we have the no island assumption, then we can prove that we can identify exactly the type by following this linking technology I just presented to you. And the main idea is really very simple. Look at here. Let's say we are wondering whether I and J are of the same type. So if this is a bunching state choice cell, then let's say U and V reveals that for us. By the bridging assumption, there's going to be an H that bridges J and U, so we know they are the same type. And same reason, G will bridge I and U. So then I is linked to J because they are both linked to U. Essentially, that's one direction of the proof. The other sufficiency comes from no island assumption. Okay, so in the last 5 minutes, I'm going to talk about the Monte Carlo. So we have tried this idea out. We wrote a computer algorithm that implements this linking technology for a DGP that has two types. And you can see that these two types imply very general forms of crossing in terms of CCPs. Okay, so before I show you the graph for this particular parametrization, I'm going to start with a different parametrization, which shows that one period ahead expected CCP, even after rounding off to the focal point, is still sufficiently different that actually it doesn't have bunching. So bunching is not doesn't necessarily happen once we have focal, right? But we actually work with a case where bunching does happen, and it happens at more than one state. So this is the self-report implied by our DGP. Here you can see the observations who have different types, okay, at machine H2 and not replace, they report the same thing. And the same happens at the H3 and not replacing. Okay. And this immediately tells us it violates our assumption B3. You have two state choice cells in which there's bunching, right? Anyone who reports in these two cells, we can't really identify their types. So what are we gonna do? So we're gonna, first approach, let's say we just drop those observations and then run Hotz-Miller on the remaining sample, okay? That's what we call discarded approach. And the second approach, following up with the question we had before, we say that, okay, let's use the expected CCPs and we form a system of equations so we can solve out the type-specific CCPs. And then we compute the posterior probability of belonging to a certain type, conditioning on your previous choices and states. Then we assign the types according to this posterior belief on types. And then this is the full approach. And you can see the results make sense. If we discard part of our sample, we're going to introduce a downward bias to the cost of replacement. So this is means the cost is slightly lower than the truth here. And that's because we're discarding machines who don't replace. So we end up having more machines that do replace, which then tells the model to rationalize it by reducing the cost of replacement. But once we do this imputation of types, then it eliminates that bias and we achieve relatively good performance without increasing the computational cost too much. Is a way to reweight. Yeah, so that's essentially what we do here full. So we reweight it by the posterior type, right? Probability of belonging to a certain type given their observed history. Using the CCPs, we actually solved from the system of equations. So that's exactly trying to still use those problematic observations. So I guess last minute, let me just conclude. I think we're proposing a quite different and novel approach to addressing the unobserved heterogeneity in the Hotz-Miller estimation strategy. It uses expectations data, and I think it's fair to say that we started working on expectations data before it's cool. But it has taken us a long time, so we are very keen to finish it off now. And we hope that this method complements other methods that relies on observed choices and states to classify the types of observations. And we are also thinking about scenarios where we can complement or add to that approach by combining the two in Monte Carlo or in applications. So that's all on our minds. So thanks a lot for the attention, and let me know if you have any comments.